Okay, let's take a look at another example. This is a really good example, and we'll do a couple of different things with it. But let's start off by assuming that we've got two iron beams. So here's one and here's the other, sitting on the bed of a truck, and the top beam is attached to the truck itself by virtue of this cable that's kind of holding it in place. The bottom beam is just free to move, I guess, other than the forces that are acting on it. And we'll say the truck has come to a stop and is now pulling forward, and we're interested in maybe what the maximum acceleration of the truck might be before the cable breaks or something of that nature. All right, so that's the idea. So what we're really concerned with is drawing force diagrams for each of the beams. We're going to do them separately because it'll also bring out a lot of Newton's third law again. So we'll start off with the bottom beam. There's going to be an mg, and I'm going to call it m sub l for lower g. So this is a gravitational force, again, due to the Earth. It will almost always be due to the Earth, acting on the lower beam. Then there's going to be an upward force, which I'll call Fnt. This is a normal force due to the truck acting on the lower beam. And then there'll be another force. This is actually going to be a normal force also, and I'm going to call it Fnb for the beams. And this is a normal force due to the upper beam acting on the lower beam. Now you might ask, how do I know that that's the force? Isn't it the weight of the upper beam? But we can't call it weight because that's a gravitational force due to the Earth, and that would be acting on the upper beam, not the lower beam. So this is not. It's going to be a force perpendicular to the surface of the beam. The upper beam is touching the lower beam, and so it can exert a force, either normal or also frictional, and we'll get to that one in just a minute, on the lower beam, right? So there's a normal force due to the truck bed, or the truck, acting on the lower beam. There's a normal force due to the upper beam. Now, what about friction? So is there a frictional force acting on the lower beam? And the answer is yes. Let's pretend for a minute that there isn't friction. There is no friction acting on the lower beam. If there were no friction and this truck begins to move forward, there's nothing so far in my force diagram that's going to push it forward or pull it forward, however you want to look at it. So there are no forward-facing forces. Don't say that fast. There are no forward-facing forces. And so friction is what is pulling it forward. So there's going to be a frictional force. I'm going to draw this one over here, and I'm going to call that Ft. All right, and that's going to be a frictional force due to the truck acting on the lower beam. And there's another one up here, and that's going to be Fb for beam, and that's friction due to the upper beam acting on the lower beam. So I've got a force due to the upper beam, one perpendicular to the surface, hence normal, one parallel to the surface, that's my frictional force. And I've got two forces due to the truck, one parallel, one perpendicular to the truck bed. That's the only thing touching the lower beam. So that's it for the forces on the lower beam. Can't talk about the cable. Cable isn't touching it. So those are all the forces acting on the lower beam. All right, let's put in an x and a y axis. No reason to use anything but our standard x, y. And I'm also going to put in an acceleration. Since the truck is currently at a stop and moving forward, the idea is that the beam will also be moving forward. So there's an acceleration in that direction, strictly in the x direction. There's no acceleration up or down. All right, now we're going to attach force equations to this as well. So let's go ahead and do those now, even though I haven't exactly talked about that. But the idea is that the sum of the forces equals mass times acceleration. Okay, the sum of the forces, and that's a vector, equals mass times acceleration, and that's also a vector. So what we're going to do is we're going to break this down into an x component and a y component. And you've done this in statics. So in the x direction, I have two forces, Fb and Ft. So it's going to be Fb, that's to the positive x direction, plus Ft, that's also in the positive x direction. And those are the only forces acting in the x direction. Now Newton's law says that's equal to ma, but our acceleration is only in the x direction, so it's the mass L for the lower beam times the acceleration of the lower beam. In the y direction, I have a couple of different forces. You can see FNT, and that's in the positive y direction. And then FNB and mg are both down, so minus FNB minus m sub lg. And there is no acceleration in the y direction, so this must be equal to 0, just like it was back in statics. The acceleration, looking at the diagram and understanding what direction things are moving, is strictly in the x direction, so there's no y acceleration. And these are the equations that we'll use then for the lower beam. All right, well, what's happening with the upper beam? So here's the upper beam, and some of the forces you're not going to be very surprised at. So there's an m sub u for upper g, so that's gravity due to the Earth acting on the lower beam. Oops, excuse me, the upper beam. And then there's a normal force. Now if we go back to the other diagram, it's going to be right here. Switch upper and lower beam. It's a normal force on the next page, a normal force due to the lower beam acting on the upper beam. I'm going to use the same lettering because it's equal in magnitude, but it's opposite in direction. So FNB is a normal force due to the lower beam acting on the upper beam. What else is touching the upper beam? Just the lower beam and the rope. So there's going to be a force over here, T. That's a tension. It's probably not a rope, it's probably a cable or a chain. So tension due to the cable acting on the upper beam. And then if I go back here and I take a look, notice this frictional force. Newton's third law says there's going to be a frictional force due to the lower beam acting on the upper beam. Since this is to the right, the frictional force on the upper beam must be to the left. And so there's going to be a frictional force in this direction. And what did I label that? FB, I believe. Yep, FB. So it's FB. So this is friction due to the lower beam acting on the upper beam. And that's it. There's nothing else touching it. So I've got a normal and a parallel force due to the lower beam. I've got gravity. That's the only long distance force here. And then I've got the tension in the cable. So that's it. There is an acceleration. It may or may not be the same as the acceleration on the lower beam. So I better label it A sub u. It's going to be to the right. And so let me also put in a set of coordinate axes. You always have to define your x direction and your y direction. And now I'm ready to write the equations for the forces acting on this beam. So in the x direction, I have T minus FB, because it's to the left, right, opposite the way it was in the other one, minus FB, and that's going to equal m in the upper beam times the acceleration of the upper beam. Sum of the forces in the y. There is no acceleration in the y direction, so FNB minus m upper g equals 0. So there's the equations of motion for the upper beam. Whether or not the acceleration of the upper beam and the lower beam are the same depends on the situation that the problem presents. There's all of the forces acting on the upper to lower beam, but let's take note. Normal force, lower beam, upper beam. Go back here. Normal force, upper beam, lower beam. That's the Newton's third law pair. And then another Newton's third law pair. I would have the frictional force, lower beam, upper beam. And over here, frictional force, lower beam, upper beam. Another Newton's third law pair. So there's two Newton's third law pairs in this particular problem. Okay, we've already talked about then the net force equals the mass times acceleration. I will mention, strictly speaking, Newton's second law, rather, is this net force. All right, so the summation here means the net force, the sum of all forces, the sum of all forces. The net force equals the derivative with respect to time of mv, which you may or may not know is momentum. If I do the product rule on this, I get the derivative of mass with respect to time times velocity plus the mass times the derivative of velocity with respect to time. Well, that's just the derivative of mass with respect to time times velocity. Notice these are vectors times ma. The derivative of velocity with respect to time, by definition, so that's always true, is the acceleration. We will rarely work with any system where the mass is changing. And so generally this term is 0 and ma is all we're going to work with. We will work with maybe one or two systems where the mass changes. This is most commonly used in rockets. But for the most part, we'll ignore that possibility. Okay, the last thing I want to talk about is inertial systems. Newton's laws are only valid in inertial systems. Now, inertial systems are non-accelerating systems. Non-accelerating systems. Now, let me give you an example of what's not an inertial system. Suppose you were right here on the bed of the truck, and the truck is moving forward, and you're just standing there, braced up and everything, and the truck hits the brakes. Now what's going to happen is you, as an observer, are going to see the beams move towards you. So the beams were initially stationary in your reference frame. Yeah, you're moving down the road, but you're staring at the beams, and they're not moving. They're stationary in your system of the truck bed. If you like, put this truck bed inside an enclosed box. So you can't even tell that you're driving down the road. Perfectly smooth travel, moving with a constant velocity. Suddenly, the truck hits the brakes. What do you notice? You notice the beams are now moving towards you. So how does this break Newton's second law? The beams are accelerating now, moving. They were body at rest. Now they're not at rest. Now they're moving. But there's nothing touching them that could move them forward. There is nothing touching the beams. The tension in the rope is 0. You can see that because the rope goes slack. Friction can't push the beams forward. It can't go from a non-sliding situation to a sliding situation due to friction. So the beams are now moving forward, but there's no force that could have done that. So the body at rest did not remain at rest. That is a non-inertial system. So an inertial system is a non-accelerating system. Technically, the Earth is not an inertial system because we're moving in a circle. As the Earth rotates, there's a big circle that we're on as we stand on the surface of the Earth. But it's a small enough effect we don't worry about it. So Newton's laws only hold in inertial systems.